Hey there, ladies and gents. Let's talk homework series 1, part 2 of 3. This is homework you received here on Monday. So we're a step behind where I wanted to be when I made this, and so no, some of the answers I'm going to provide for you are actually going to be more explained in Wednesday's class, which isn't a bad thing. So if you want to get a little bit ahead and you're working on this, you're going to be just fine. So just keep on working. All right, so let's get into it. So we want to find some zeros again. And so this hopefully is becoming second nature, getting a lot more comfortable with it. So you know the very first thing we have to do is set the function equal to 0, because zeros only make sense if you are indeed solving for 0, the value to be 0, excuse me. And now we're left with this function. So in terms of being able to factor it, it doesn't look like I'll be able to, simply because I can't think of two numbers that are going to multiply to 34 and add to 10, at least not off the top of my head. So I think I'm going to go into just completing the square instead. And so I'll subtract 34 on this side to leave myself room to pick a new c. So I have this 10x plus some value here. That value is going to be 25. So completing the square, remember we're going to take this negative 10, break it up over a square over two binomials, and so we're going to have it. So negative 10 will have to negative 5, which will be our new binomial. So we're looking at x minus 5 squared, and then I'll have to compensate by adding 25 to this side. So if I take 34 and negative 34, and I subtract or add 25 to it, excuse me, I should be left with negative 9. So then now my task is to solve for x. So I'm going to go ahead and square root both sides. On the right, I'll have x minus 5. On the right, I'll have square root of negative 9. And so you might be asking yourself, well, what in the world do I do with that negative 9? Hold on, let's keep solving first. To get rid of the negative 5 to get x by itself, I'm going to add 5 to both sides. And so my answer at this point will be x is going to be equal to the positive negative values of square root of 9 plus 5. Square root of negative 9, excuse me. And so here's where our dilemma is. Here's where the idea of imaginary or complex numbers comes into play. Because what you're actually looking at are a set of complex roots. So being a quadratic, you're guaranteed two roots. In this case, your roots are going to be as listed. So this is going to be the quote-unquote answer. Now we don't want to leave it like this because it's improper to leave a negative square root value. So here's where the idea of I comes into play. So again, we're going to talk more about this on Wednesday. So if this is kind of confusing to you, hold until Wednesday's over, and it'll make a little more sense. Because after Wednesday, you'll see that this will actually be equal to plus or minus 3i plus 5 to be our x's equal to x. And that's the answer in the form that I would expect. If you want to bust them up, you can. So x is equal to 3i, let's write it properly, 5 plus 3i, or x is equal to 5 minus 3i. Okay? And so again, if the I is a little confusing to you, hold those questions till Wednesday, and then we'll see a little better how I'm getting that, and hopefully also what it means. So let's go into this now, nice little cubic. So 0 is going to be equal to x cubed, and I'm going to go ahead and rewrite 27 as 3 cubed. So we can use the sum of squares here, where a is x, and b is going to be 3. Okay. So our sum of squares formula, is going to be a plus b times the quantity of a squared minus ab plus b squared. And so plugging into that value, the values that we know, we're going to have x plus 3, and then we have x squared minus 3x plus, what's that, 9? Okay. So in terms of finding our zeros, we get one for free. We have this x plus 3, which will give us a negative 3 for that. Now to find our other two, let's go to Desmos really quick. Let's see what our quadratic looks like. And let's see if it's even viable to try to find this particular zero. And so our main quadratic, as Desmos loads, that goes. Okay, so okay, so our main quadratic is going to be, let's see, x squared minus 3x plus 9. And so you can look here, again, we're going to kind of this weird situation where the zeros we have left are not going to be on our axis. Now, before you kind of recalled what it means to be a complex number or an imaginary number, this is going to be a difficulty for us. But now we have a little more knowledge. Let's go ahead and proceed forward with the knowledge that what's going to go here is not going to be any kind of real number, but instead a complex or imaginary number. So let's do some different color. So let's go ahead and solve this quadratic kind of separately. I'm going to complete the square again because I think that's probably the fastest and easiest way to do this. So we'll have x squared minus 3x equals negative 9. So we're kicking that 9 over. So we're going to have x minus 1.5 because that's half of 3. So when you break it up over that box structure, it'll be 1.5, 1.5. So this will be negative 9 plus 2.25 because that's what 1.5 squared actually is. So we have x minus 1.5. Let's do a little cleanup. We have 9, negative 9, and then we add 2.25 to it. We get negative 6.75. Okay. So we square root both sides. We'll end up with x minus 1.5 is equal to the positive or negative square root of 6.75, excuse me, negative 6.75. And so we'll have our values to be 1.5 plus or minus the square root of 6.75 I, which is okay to leave it in this form because that's, although it's not what we call it in exact form, because it's a little bit weird to leave a square root or a decimal number a square root. For these purposes, it's acceptable. So our roots are going to be negative 3, 1.5 plus square root of 6.75 I. And then we're going to have 1.5 minus square root of 6.75 I. Okay. And so our added knowledge of complex numbers and imaginary numbers allows us to solve and find all three roots, one of which is real, two of which are complex. All right. So the idea of a complex zero versus a real zero, I think the big thing that we'll see in class is it's really where its placement on the graph is going to be. So there's a student that kind of mentioned that if you think about a zero as a change in direction or a change in sign, which indicates a change in direction, we can start to look at a graph kind of in a different way. So anytime we kind of see a weird saddling or a change in direction, even if it's not going to be around, say, like an axis, we can say it's going to be a zero. But again, we'll talk about that more in class on Wednesday. Let's talk about number sets. So with that being said, complex numbers are any numbers that can be expressed in the form of a plus bi, where a and b belong to the real numbers, and I is imaginary. And when we say imaginary in this case, remember we're saying that I is precisely equal to the square root of negative 1. So a number that we can't express in real numbers, but we can intimate in this form. Positive numbers, well, positive numbers are going to be anything, of course, that's going to be bigger than 0. An interesting way to write that is to use the integer notation with a plus sign here, or integer notation with a plus sign here, meaning that we're talking about numbers that are bigger than 0. Now, of course, we're talking just about whole numbers. If we're talking about real numbers, we can talk about real numbers or real numbers. Okay? So it just gives you an interesting way to kind of write that set without actually having to explain it out, that they're just numbers that are bigger than 0. In terms of even numbers, now this is really interesting too, because we could say, like, as a list, it's going to be like 0, 2, 4, 6, 8, or should say 2, 4, 6, 8, 10, 12, 14. We can also think really carefully about how even numbers can be generated. And so if I give you any number, just like pick a random number like 5, the question is, well, what do you do to 5 to make it even? Now, you could say two things. One, you could say, well, you just need to add one number. But that's not always going to work. And so if you say the rule to get an even number is to simply take a number then add 1, what happens when you're given an even number, like 7, or I'm sorry, like 8? You add 1, it becomes 9 non-number. So the rule for generating evens can't just be take a number then add 1 to it. But again, go back and think about any random number like 5. What else can I do to it besides adding 1 that will ensure that it's an even number? Now, if you think about that really carefully, the solution you could arrive at is to multiply by 2. And so, like, for example, if you choose any number like 8, and let's say you don't know if it's even or odd, but if you multiply it by 2, that becomes 16, which is going to be an even number. Another example, choose another random number, let's say 7. I don't know if it's even or odd, but if I multiply it by 2, that's going to be 14, and that's going to be an even number. Now, uh, that leads us, if we want to generalize it, to a rule that if you pick any number n, where n belongs to like a real number, then 2n is even. Which means the key feature here is if you take any number and multiply it by 2, you're guaranteeing it to be even. You're not guaranteeing a value, just the fact that it ends up being an even number. All right. Now, if you remember the last video or the last key that maybe you looked at, we talked a lot about how the vertical line test is an okay thing to think about visually, but can't be your only explanation of whether or not you know something's a function. And so starting with the vertical line test, it certainly fails over and over again. But the important thing is you understand why it fails. And the big reason why it fails is because it violates the basic idea of what it means to be a function. Remember, a function is defined to be one x value maps one y value. In this particular case, this one x value maps both two different y values, which means it violates the rule of function. In fact, it does it pretty much every single point along its domain. So if we stop here, we'll notice that if we have x equals 1, it maps both 1 and negative 1 to the y. So this is a 1 to 2 function, or sorry, 1 to 2 mapping. And functions have to be a 1 to 1 mapping. 1x goes to 1y. And so this is not a function. And the reason being is because at least one point, you have one x value that feeds into two y values. That's no good. That's not a function. Right. Keep cruising here. All right, we want to find the domain and range in the following situation. You started with $600 for gas money at the beginning of the year. Each time you fill up, you spend exactly $30, which includes tax, because you're very consistent. You spend the money only for gas and spend until it's all gone. Okay, and so the first thing we have to understand is what thing maps our x, which thing maps our y. So in other words, what's our independent variable and what's our dependent variable. So a good answer would first initialize those variables. And so we have to let x be, in this case, the number of times you gas up, which means we're going to let y be the amount of money left. Okay. Now you can get this by simply kind of asking yourself, like, what calculation would you perform? So if you gassed up one time, that'd be $30, which means you're going to have $570 left. If you gas up 3 times, that's $90, which means you're going to have $510 left. And so you think about that calculation, I'm taking the amount of times I gas up times 30, and I'm taking that total from 600 to tell me how much money I have left, which is how I'm getting these two variables. Now, in terms of tracking the domain and range, let's use some proper set notation here. So the domain in this case is going to be the set of all x's. And if you think about how many times you gas up, you got to be really careful here because we can't write this as like a range. Okay? What we can do is make a list. So we can just make a list of all the possible times you gas up. Now there is going to be an upper limit to this domain. There's going to be a time where you run out of money. So if you can spend $600 and you're gassing up 30 at a time, you can only gas up 20 times. So that's going to define a domain. So it's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 14, 15, 16, 17, 18, 19, 20. Now that's very tedious. And so I'm going to give you kind of another way to look at the domain now that we have a little knowledge of like number sets. If you notice and look at all the numbers I'm actually using, those are all integers. They're integers that are going to be between 0 and 20. And so we could also write our domain like this. All x's, such that x belongs to the integers. Oops. Remember, integers was at z. Integers are going to be all the positive whole numbers, including 0. So right now, I've restricted all, like, I've taken away all the decimals, all the fractions and stuff, just by saying, hey, look, consider x's that are only integers. And then I can define where x is going to be less than or equal to 20. I don't have to define it to 0 because integers aren't part of 0. I'm sorry, integers include 0, excuse me, and not negatives. So I don't have to say like from 0 to 20. I can just say pick all the integers that are less than 20, and that would be the exact set I wrote above. And so you can kind of see why having knowledge of these number sets is a good thing, because it allows you to actually write a domain very, very nicely. We can do a similar thing for range, because what you're going to find with range is that it's going to be all the y values that start at 600 and decrease by $30 at a time. Okay, and so we can dot 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 until we hit 0. Okay, and we can write the full set here. The other thing you can do is define it using integers, although I think this notation serves the same purpose. And so when you're writing domain and range, if you have some knowledge of these number sets, it can make your job just a little bit easier. All right, now we're asked to find domain and range again, this time of this function. So if you're looking at this function, domain and range, we have some blocks here because domain and range will not be just continuous. And so it looks like there's some values that we cannot take. And so as far as our domain goes, we have this nice vertical asymptote at 2, which means we can use all these values that don't include 2. And then for our range, it looks like we're not going to ever quite be able to use 1. And so we need to kind of reflect that in our domain and range writing. And so I'm going to switch things up, and I'm going to use interval notation to express my domain and range. And interval notation, remember, is going to use like the brackets, one or the other, where these mean we cannot use that number, and then these means we can use that number. And you're also going to see a union, or a U. Remember, that union means put together. Okay, so when we talk about the domain, we're certainly coming from negative infinity as far as that end behavior, and we're certainly going to infinity as far as that behavior, or positive infinity, excuse me. So the only number we can't use is 2. And so the way I'm going to write this domain is that we start at negative infinity, we go to 2, we can't use it, so I'm going to use a round bracket, and then we resume our domain again at 2, and then go to infinity. And so that's just another interesting way to write it. You could use like the other set notation and say like all numbers except for 2, but I want to switch things up, keep it fresh, and write this way as well. Okay, so let's talk about range. We're going to experience a similar thing in range because we see the range end behavior going to negative infinity, and then this end behavior going to positive infinity. But we're not going to be able to use this value of 1. And so we're going to see like a negative infinity to 1, can't use it, resume at 1, and then go to infinity. And so again, that's kind of another interesting way you can write domain and range. That's not going to be just the normal set notation. Okay. So let's go to some ACT prep. If m and n are integers, which means they're going to be whole numbers, non-negatives, which of the following must also be an even integer? Now the key term here is even. And so the question is, if I just pick 2 numbers that are whole numbers, which of these are going to be guaranteed to give me another even integer? And so we have some interesting things here, but if you understand the rules of even numbers, and I'm going to flash back up here, the key feature is that if I multiply a number by 2, it's guaranteed to be even. We can quickly answer the question to be A. So you can do this by like example, just simply picking numbers. But the way we can think about it is that if m and n are integers, that means m times n is an integer, which basically means that we have 2 times an integer. And 2 times an integer is guaranteed to be even. The key feature is this multiplication of 2. N times n is not guaranteed to be even. A good example would be like 7 times 5. Like 7 and 5 are both integers, but when you multiply them, you get an odd integer because neither one is 2. Same thing with the plus 2 minus 2 thing. Yeah, that could end up being positive, it could end up being negative, but you're not guaranteed to be it because, again, if you think about my original example, Like if you just pick a random number and then add 1 to it, half the time it's going to be odd. And then same thing for 3. 3 doesn't guarantee any kind of even movement whatsoever. All right, last ACT prep question. In the equation, x minus a is equal to y minus a. Let's say that's true. Which of the following must also be true? Okay. Now this is going to be a tricky one. So we have x minus a is equal to y minus a. And a lot of these are going to be true some of the time. And so my thought here is to scan all the answers and see if we can pick out one that we know must be true all the time. So the one I'm going to point to is going to be this one at the bottom. Now some of these other ones are true quite a bit of the time. But the reason my eye went to this one first is because if you look, oh, come on, highlight, there we go. If you look at this compared to the original, these are actually the same statements. Here we have x minus a, here we have negative a, oh sorry, wrong one. Here we have x minus a and negative a plus x. These are actually the same exact statement. They're just switched around, but if you notice the sign carried with the a, so they are literally the same exact statement. Same is true for this y value. And so since I know they've just been switched around, I know this is guaranteed to be true without question. Now, I'm not saying some of these other ones aren't really close or aren't for the most part going to provide you good answers, but I know for sure A is going to have to be the same because they're the exact same statement. Ergo, I'm going to pick that one because being the ACT, you got to pick the best answer, and there's only one answer. All right, guys, that was a long video, but that covers key number 2. One more to go before the end of the week, and our quiz on Friday.